we're going to talk about model specification. Remember, for the purpose of model specification, you need to understand what kind of error in specification there are covered in the curriculum, and more importantly, what does it do, what effect it has, what effect does the misspecification have on the outcome, on the output of the regression result. So, happy learning. Model specification is two types. One is selection of explanatory variables, meaning choosing the right X variables. For doing that, the analyst has to have a firm understanding of the economics of the dependent variable, the Y variable. What are unscaled data? Instead of that, I want to do a proportion 0, or the mean is 0. But at the end of the day, the X2 and X3, that is also a problem that will. Alright friends, now finally, the extensions of multiple regression. So we went through this whole process of identifying a linear model that helps us in generating a good quality forecast for our variable of interest, which we call the dependent variable, also labeled as a Y variable. Now, in a multiple regression, we use multiple independent variables, multiple X variables. All right, so now we are going to talk about some extraneous aspects of this multiple regression model. First, we'll talk about influence analysis. If our data set has extreme values of X or Y in our sample set, in our observations, then we say that there is a possibility that our estimated coefficients, which may be beta naught hat, beta 1 hat, and so forth, all those regression parameters, they will be estimated inappropriately, inaccurately. And if your estimates are inaccurate, your forecast is going to be inaccurate or lousy. Now, there are labels that we assign. This is what the curriculum wants you to know. So the labels that we assign for extreme values, either too high or too low, of X variable, or also known as the independent variable, and that label is called as a high leverage point. So if you one of your X variable value, say for example you have 3 X variables in your model, X2 for a specific observation is way too high, outside of the range, outside of the normal range. Well, what does it do to our regression model? Will it alter the coefficients? And keep in mind, just because X2 is a high leverage point, it doesn't necessarily always mean that only the impact of that will be on estimated beta 2. So it could affect all the parameters. So we just don't know what impact it would have, but we would be concerned because it does affect your estimates of your parameters. Similarly, another label that we need to know is known as an outlier. This refers to extreme values of the Y variable, also known as a dependent variable. Now, how do you detect if a specific observation is considered too extreme? And so for X variables or high leverage point, what we do is we calculate leverage. You're not going to calculate for the exam, so don't worry about calculation part of the leverage. It is going to be given to you if you're going to use this data. It is simply a standardized metric of distance between the value observed in that observation. So x2 is equal to 349 for a specific observation, for the 10th observation, say for example. Well, is it extreme? Is it high leverage? Well, we first calculate leverage for every single observation, every single x variable in our sample set. And then that's leverage, by the way, is again standardized metric, which has a value between 0 and 1. All right. And if it is too high, if it is close to 1, then we say it is a high leverage variable. How do you determine that? What is too high? Well, your cutoff point is 3 times k plus 1 divided by n. So just plug in the value. Remember, k is equal to the number of x variables, independent variables in your model, and n is the sample size. So we just plug that in. Say, for example, k is equal to 3. So 3 times 3 plus 1, and let's suppose n is equal to 20. I'm just making up numbers as I go along. So it is 3 times 4, or 12, divided by 20, or 6 over 10, which is 0.60. And so that is your cutoff point, given the values of k and n as suggested in my example. So after we identify which observations are high leverage, then we need to critically evaluate whether is it because that actual observation was valid, it was representing some turbulent times in the market, or is it simply a fat finger error, meaning the person that input the data made a simple keyboard error. Now, for outliers, remember outliers pertains to the y variable or the dependent variable. We calculate what is called as studentized residual. The way we go about calculation of studentized residual, even though you are actually not going to calculate it, just understand the process. So, say for example, our sample size is 24, and so we delete one observation, meaning let's say we delete the first one, okay, and then we will have 23 remaining observations. You estimate your regression model using those 23 observations, and once you estimate a regression model, you will get y is equal to beta naught plus beta 1 x1 plus beta 2 x2. I'm just going to assume 2 x variables. And so what you're doing is fitting or estimating the values of beta 1, beta 1, and beta 2 using 23 observations. Once you do that, once you find out the values of beta 1, beta 1, and beta 2, you calculate the value, the forecasted value for the first observation. That's the one we deleted. So we calculate that value. Let's say, again, remember the one observation we deleted had a y value, had corresponding to x values. So we just use those x values in our equation and forecast the y variable. And then we subtract from the actual y variable and calculate the residual for the first observation in a model that excluded that observation. And that is called as studentized residual. Well, that is a residual, and then we calculate the studentized residual for each residual that we calculate. For each of the observations in our data set, 24 observations, you have 24 residual, and then you calculate the studentized residual, which is basically standardized using a process. Now, you are not, as I said, going to calculate studentized residual. This will be given to you if you are going to evaluate if there are outliers in a sample set. Now, we check the studentized residuals vis-a-vis a t-statistic. So studentized residual has a student's t-distribution, hence the label studentized. So we typically use the label t-stat or a t-distribution without its actual name, which is student t-distribution, right? And that is where the studentized residual comes into play. So we are the studentized residual have a t-distribution, and if residual exceeds the critical t value, we are only looking at one side, even though it is really a two-tailed test, because it is symmetrical. So looking at both sides is redundant. You know, if you're going to reject it on the left side, you would automatically reject on the right side if you had used the absolute metric. So the degrees of freedom is going to be now n minus k minus 2. The critical value that you look up from the t table will have n minus k minus 2 degrees of freedom. And why is it now n minus k minus 2? Remember, we use typically n minus k minus 1 for t-stat. Well, that is because we lost one observation. Remember, we started out by deleting one observation. So now we have one fewer observation when it comes to degrees of freedom for the t distribution. All right, let's look at a quick example of using this studentized residuals in identifying outliers in a data set. So you are given a researcher is examining a regression model predicting the 3-day return on IPOs using 3 explanatory variables. So K, the number of degrees of freedom, the K, the number of X variables is 3. And the training sample consists of 24 IPOs, that is N, the sample size. The following exhibit shows basically you're given the studentized residual directly as expected, and a partial t-table will be given to you as well. I have not included that, but which observations are considered using 5% level of significance. Now, the 5% again, that is the only partial table that is given to you. So remember n minus k minus 2, and that is 24 minus n k is 3 minus 2, we get 19 degrees of freedom. And we wanted, again, 5%, which is already, the excerpt given to us already for 5%. All right, so 19 degrees of freedom is 2.09. That's your critical t value. Now you're going to compare it to the studentized residual. And again, absolute values of studentized t residual. Either the value is less than negative 2.09 or greater than positive 2.09. And so you see the third observation, that is exceeding the threshold of 2.09. So that is considered to be an outlier. Now, going down the list, I see another one, observation 23 is positive 2.18, again exceeding the threshold of 2.09. And then observation 19 has negative 3.0165. Again, if I take the absolute value, it does exceed 2.09. That's what you are going to do. So standard hypothesis testing, if it exceeds the critical value, you reject it. Remember, we take only absolute value because of symmetry in the t distribution. So that is the detection of outliers. Going on, we are going to talk about qualitative independent variables or qualitative X variables. These qualitative X variables are called as dummy variables because the numerical value assigned to it is meaningless. It does not carry any significance or meaning to it. They are dummies, or they are basically non-information carrying values. So when you have a qualitative variable, for example, month of the year, we assign a value of 1 to January 2 to February 3 to March and so forth. But the numerical assignment does not have any actual interpretation, meaning June is not necessarily 6 times as important as January, just based on the number assigned to it. So dummy variables are qualitative variables, and we want to assign a value to it. And the value that we're going to assign is either 0 or 1. 0 indicating no, 1 indicating yes. So if, for example, we are using dummy variable of emerging market versus developed market. Now, one key takeaway, there are 2 key takeaways here. One is that always use n minus 1 dummy variable. N is the states possible. In this case, n is equal to 2. The 2 possibilities in a our data set, either the data belongs to emerging market economies or the data belongs to developed market economies. So n is equal to 2, we are going to use only one dummy variable to denote that. If it takes on a value of 0, we say it is equal to emerging market. If it takes on a value of 1, we say it is developed market. I mean, I'm assigning those values 0, 1 arbitrarily, it doesn't matter. We'll see as we go to the next important aspect, and that is the interpretation of a model that uses dummy variables. So again, we are recognizing that the behavior of the relationship between y and those x variables is conditioned upon existence of categories in our data set. So the behavior of, for example, returns in emerging market is different than the behavior of returns in developed market. If that is true, if that is something that we can theoretically justify, then we need to include dummy variables to capture that fact. So dummy variables allow us to categorize data in our sample so as to recognize that the behavior would be different if you try to use one whole data set and not categorize it. You are going to get a less than perfect model. You're not going to get a good model. So now the dummy variables can be used to alter the intercept, the slope, or both. And when I say alter, it is basically to capture the relationship in the data. So if we see a systematic pattern, I want to capture that pattern. Again, our objective is to forecast y variable. We want to capture the pattern so that our forecast is going to be most informed, most accurate. So it can change the slope, the intercept, and or both. Now, the interpretation is the key. So you are given a specific model that uses dummy variable, you need to be able to integrate the model. That's what we are concerned about. You are not concerned about actually coming up with the model. So I'm going to use one dummy variable to illustrate this, and it's more possible to use only one. If you add more than one dummy variable, it can get fairly complicated. Remember, my objective is to pass the damn exam, not to become an expert modeler. So I'm going to concern myself with only a single dummy variable. Again, D is capturing whether the data belongs to emerging market or developed markets. Now, in the intercept dummy, so I have the D variable capturing the dummy variable, and I have your regular X1. Let's say Y is return, X is GDP growth, and we are trying to model the relationship between GDP growth and market return, index return for that market. Right? So now if D takes on a value of 0, that's your emerging market, then in that case, that entire term drops out. Or if it takes a value of 1, then it becomes simply beta 1. And notice, now beta 1 is a constant for that category, for the category of developed markets. And it is basically resulting in shift of the intercept term only, doesn't alter the slope. So beta 1 is simply the distance that is above the original slope, original line, and the original line is for when D is equal to 0 over emerging market. So you have emerging versus developed market, and we see a specific pattern. Maybe the returns are higher in developed markets, and therefore the entire line, this is the linear equation, so straight line, shifts upwards. The second type is the slope dummy. Again, we are capturing that with a single variable D, that is the dummy variable. And notice now I have an interaction term. D is actually multiplied to the X variable. So you have the traditional X variable with its associated slope coefficient, and then there is an interaction term. And that interaction term captures the changes in slope on account of the dummy variable. So But we see that here the slope increases on account of whenever d is positive. When d is negative, that entire interaction term. Sorry, when the d is zero, the entire interaction term drops out. And our equation becomes this basic beta naught plus beta 1x. All right, and then the last one is the intercept, and there is a change in intercept as well as change in slope. So you have the intercept dummy as well as an interaction term, and now you have changes in intercept as well as changes in slope. So depending on the type of model that is presented to you, and again we are only concerned with a single dummy variable takes on a value of 0 or 1, we just plug in the value of 0 or 1 in your equation to determine and answer the type of question they are asking you. So nothing fancy, just linear algebra. So qualitative dependent variable, now we are looking at the y variable that is the dummy variable. And say, for example, you are trying to forecast the probability of default on for a company bond issue. So there are two possibilities. It's still a dummy variable, 1 or 0. Default, we did note as 1. No default is 0. We can choose default as 0 and no default as 1, but we need to be clear when we set up the prompt. Now, the issue here is we can't. all, again, for the purpose of the exam, so we're going to assume there is only two categories for y variable and only one dummy variable. Now, it estimates the probability, or specifically, it estimates log of the odds. And what is odds? So, probability is the probability of an event success, probability of an event occurring. And so, you take probability divided by 1 minus p, that will give you the odds of that event. So, that instead of using probability, we are using log of odds in our as our dependent or y variable. Right. Now, our interpretation, so y variable is log of odds. That's your y variable. And your notice the right hand side is exactly the same as the standard linear regression equation. Now, once we estimate the log of odds, then the probability can be reverse engineered as simply 1 divided by 1 plus e raised to negative forecasted value of y. So if I have x values, I can plug those in my regression equation. When I plug this in, I get what? Y hat. And then I use that y hat in my equation to estimate the probability. So, we'll look at an example to make things a little clearer. But the idea is the right-hand side is simply a linear equation. Just like before, we're going to plug in the values of x's and estimate y hat. And once I have y hat, I can estimate the probability using this equation, 1 divided by 1 plus e raised to negative y hat. Now, the interpretation of beta, not the intercept term, in this context is simply what? That it is the log odds when everything else, when all the x variables are 0. So you'd be left with the intercept term, and that would be beta naught. But again, the interpretation is not probability, it is log of odds of whatever we define the event to be. Now, the slope coefficients, beta 1, beta 2, and so forth, those requires us, because remember the underlying relationship, even though the right-hand side is linear, even though right-hand side appears to be simple linear equation, the actual relationship is not linear. So this, because of the logarithmic function, so you will see a curved line representing this equation. So if you want to look at the interpretation of betas, that interpretation changes depending on where in the curve you are. It's kind of similar kind. It depends on where on the curve you are to interpret the slope coefficient. We'll see how we can still interpret it. We are going to use first the average values of the variables, the x variables. We're going to use the first the average values of the x variables and calculate y hat, and I'm going to do x bar. Basically, y hat calculated using the average values of x variables. Then I'll change one x variable at a time. So only one x variable, I'll increase or decrease by 1 unit and re-estimate my y hat. And then I can basically, remember, once I have y hat, I can calculate probability. So I do the calculation of probability under both scenarios using average, using using a tweak by 1 unit, and the change in probability as I tweak that 1 unit. Now there is this, software packages, and one of the things that you need to be aware of as far as exam is concerned is to be able to interpret software output. Now pseudo R square is, your traditional R square is not applicable in logistic regression, so they present with pseudo R square. Pseudo R square is just like R square, higher value indicating better fit. However, we can't compare when using R square. We need to be cognizant of the fact that you can't use R square when you change your dependent variable, right? Dependent or y variable. So you can't just take two separate models with two different y variables and compare their R square. R square is only used to compare iterations of model that try to explain, that try to forecast the same y variable. So they are basically used to competing models with the same dependent variable. In that case, we can say the higher R square is a better fit. Right? So same principle applies for pseudo R square. When you're given the pseudo R square, three different models with the same y variable, you say the one that has a higher pseudo R square is a better fit. So here is an example of a logistic regression, and you are given that you are trying to estimate the likelihood of dividend increase. And we are not estimating percentage increase, then it would become a continuous variable, not a categorical variable. We could use standard multiple regression in that scenario. Here we want to say whether it is an increase or not an increase. So increase is 1, 0 is not increase. Okay. You collected the historical data, and the three variables that are used in this model is age. Age is the number of years since the last increase in dividend was made. The second variable is the amount of free cash flow to equity So remember, probability is equal to 1 divided by 1 plus e raised to negative y. And if all these variables, age, FCFE, and cash, all those other three x variables are 0, then the probability of a dividend increase will be equal to 1 divided by 1 plus e raised to 2 negatives cancel out, so simply 3.445. Now the p-values given to us are simply for statistical significance of those estimates. So remember the interpretation of p-value, if it is less than alpha, alpha being the level of significance, p is less than alpha, then we reject the null, meaning we say that it is statistically significant. Now the intercept is statistically significant, its p-value is 0.002, which is less than 1%. Remember, so 0.002 is obviously less than 0.01. And so we say, yeah, it is significant at 1% level. Now, the other variables are not significant at 1%, but FCFE and cash are significant. They are less than 5%. They are not less than 1%, but they are less than 5%. So they are significant at 5% level. Age, its p-value is 0.412. It would be significant if you set your alpha to be 50%, but that is not reasonable. Any alpha beyond 10% would mean the model is crap. So level of significance, normally we set 5%. Be more conservative, you set 1%, but we're not going to go as high as 50% to try to say that age is a statistically significant factor. All right. Now, we already said the intercept term is statistically significant. Now, calculation, if I plug in the value of e raised to negative 3.445, I get basically the log odds. I get the log odds, and then I take the probability, which is odds divided by 1 plus. I could just done this with e raised to 1 plus e raised to 3.5, and that'll give you 3.09%. The probability of dividend increase, assuming all other variables are 0. So that is the significance of intercept term. Now, let's talk about the other variables. Now, remember, you are given the averages for the variable. So we're going to plug in those values in our model. We are given the model itself also. So I'm going to start with negative 3.445. So log of odds. And that is your y. And plus, so age times its coefficient, 3.20 times 0.332. Now the x values I'm plugging in 3.20. Remember, that is the average. That's x bar or x1 bar plus 0.08 times 12.33 plus 0.03 times 3.21. I need to be careful with the signs of the coefficient. They are all positive, so I don't need to have a negative sign in my equation here. And this will be my y hat. And if I plug in, I'll get a y hat of negative 1.299. This is using average values of the independent variables.
Okay.
Plug that negative 1.299 in my equation. Remember, again, the equation calls for e raised to negative y hat, so two negatives cancel out, becomes e raised to positive 1.299, and that'll give you a value of 21.42%. So at average values, the probability of an increase in dividend is 21.42%, average values of the x variables. Now we're going to tweak only one, and we're specifically asked in this case to tweak it by 1 unit, so go from 0.08 to 0.09. And plug in, the only change in our equation is instead of probability that you get is 23.57%, which means an increase of 2.15%. So even though the coefficient is 12.33, 1 unit increase in FCFE does not mean 12.33% increase in probability of given an increase. It simply increases the probability by 2.15%. So that is your interpretation of the slope coefficient in a logic model or logistic regression model. Now, nested logistic model. So the nested logistic model is basically similar to our nested multiple regression model. Remember, we had unrestricted model, let's say that had 3 variables, and then we remove one or more of those 3 variables to create a restricted model. Same thing in the for the logistic regression. In our example, we have 3 X variables, age, FCFE, and cash. Now we are removing one or more of those X variables, and that would be a restricted model. Now, for our purposes, we are going to be given what is called as log likelihood metric. Now, this metric has a negative sign, and higher values indicate a better fit. So for a restricted model, if you are given 2 models, unrestricted meaning has more X variables, restricted meaning has fewer X variables. There are Q variables removed, and you are given an output the log likelihood metric for each of those 2 models. You take the difference and multiply that difference by -2, and that has a chi-square distribution with Q degrees of freedom. So chi-square distribution with Q degrees of freedom. Remember, chi-square is 1 tail. So as long as your chi-square statistic omitted variables are useless if you reject the null hypothesis, meaning if your calculated chi-square statistic is greater than the cutoff point, the critical chi-square value. All right, friends, as expected, and a partial t-table will be given to you as well. I have not included that. You are given a specific model that uses dummy variables.
Hello, CFA friends. Well, in this module, we're going to be starting a new quant topic. It's going to be time series. And in this first module, we're going to start to look at linear and non-linear trend models. Okay, so let's get started. So, financial. Data can be difficult to model using conventional multiple regression. So that's why we now want to turn to time series. And there are two broad families of time series models here. So the trend model is where the independent variable is going to time. Okay, so you probably can guess that easily because of the name time series. So independent variable is time. And within that family of trend models, we can have further two subdivisions. Linear trend model is where the dependent variable grows linearly over time. I'll give you examples of that later. And log linear trend model is where the variable grows exponentially over time. Again,
Hey, I have questions. You can just ask the question. What are you guys busy with? Are you studying? Are you working? We're gonna be done at like 10:30. So we've got an hour to go.
late. So this is what's considered probably the easier section of time series, and that's what we are dealing with anyway in this particular module. And then you've got the lagged models, the autoregressive models, where there's no distinction between dependence variable being y and independent variable being x.
sense.
change
Changes,
in
yeah.
linear trend model coincides with the value of slope. And this all you gotta know here for the linear trend model. Now upping the level of difficulty one notch, we're gonna move into the log linear trend model. Before we look at this, I want to explain why we're looking at this. So I'm gonna go to the whiteboard here. And if I just basically take the dollar sales of a successful company and I model this over time, what I might probably see is instead of seeing a straight linear growth in the sales, I might actually see something like that. Curve growth, which we will refer to as exponential growth. But the same will also apply if in that savings example you were taking $100 every month, but instead of putting it under your mattress where it would earn you no interest, if you were investing it in some sort of vehicle, let's say you can find a vehicle that will generate 10% of return per annum. Well, if I'm starting with $1,000 at the end of the first year, I will have $1,000 at 10%. Well, at the end of the first year, this is times zero, of course. At the end of the first year, I will have $1,100, which is 1,000 times 10. Now, at the end of the second year, will I have $1,200? Will I simply add an additional $100? Well, no, because here what I'm going to actually experience is the power of compounding, or compound interest. What I'm going to do is I'm going to earn 10% of the 1,000, which is 100, but I'm also going to earn 10% on the interest that's already in my account from the end of year one. So in fact, it should give me 1,210. So that's 1,210 more or
Equally.
less uniformly
Yeah.
clustered around our regression line.
Yeah.
Well, they aren't in this particular case. You can see here that there will be a lot of dots persistently below the line or persistently
Above the line.
above the line. This is an example of positive serial correlation, and we can test for this via the Durbin-Watson test. Okay, so use the Durbin-Watson test here to test for serial correlation, and if serial correlation exists, obviously the model on the left-hand side of the picture, the left-hand side of the slide is incorrectly specified. So how can you fix that? Well, the answer is if you believe that what's causing the serial correlation is coming from exponential growth, as it may be the case here looking at the shape of this scatter plot, then the easiest way to fix the problem is to take the natural logarithm of y. And in fact, that's what we've done here. We've made this transformation, and now we can see that the dots are uniformly scattered around the regression line. And of course, if you want a more formal test here, we can rerun our Durbin-Watson test and see that serial correlation is no longer present. And once that's done, we can then use the model to predict the future. So regression errors in current periods must be uncorrelated with errors from other periods. Okay, so this is just one good old regression assumption.
Hey, Mr. Walker. I'm from South Africa. Oh, I'm talking alone. There's no one here. I'm gonna end the live, guys. This has been very productive. And yeah, it's time to log off.